Let's say we are trying to calculate outputs, not just for a single input, but for multiple inputs. So let's say we have two inputs, x1 and x2. Okay, and these again are vectors. So they're, and we want to calculate together. So let's go ahead then and create x, which equals x1 as the first row and x2 as the second row. So if we multiply it by w1, normally we would be coming out with a 1 by whatever the second dimension of w is. Let's look at a particular example of this. So let's say x1 is 1, 2, 1, 2, 3. So x1 is 1, 2, 3, and x2 is 3, 4, 5. Then in this case, x would just be these x1 times w1 plus b1. So that's going to be equal, let's say, single matrix 1, 2, 3, 3, 4, 5, times w. What do we know about the form of w? Well, we know that it has, since this is a 2 by 3, it has 3 rows and as many columns as there are outputs. Let's say there is one output. So w is going to look like this. And this is 0, 1, negative 1. When we calculate this, and I'm going to ignore the adding beat, we'll just kind of ignore that for a moment. So what we end up is, so this is a 2 by 3, and this is a 3 by 1. So we're going to end up with a 2 by 1. 0, 2, negative 3 is negative 1. 0, 4, negative 5. That's a shame. Let's just change this one to 6 so we get different values. 0, 4, negative 6, negative 2. So that says that the multiplication by this weight matrix, we had two inputs, and we actually got two outputs here. And we can continue this throughout. So normally what we were looking at is that z sub I, if a sub I minus 1 is a 1 by, let's just say n, then a sub I minus 1 is a 1 by s sub I minus 1. Then a sub I is a 1 by s sub I. So if we have one training instance, a sub I minus 1 is a 1 time by s sub I minus 1, and a sub I is a 1 by s sub I. Just like if we had one training instance, then the input here was a 1 by 3, and the output would have been a 1 by 1. However, if we have k training instances, then all of a sudden, the output of the previous layer is actually k times s sub I minus 1. And the output of this layer is k times s sub I, k by s sub I. Right, so the number of rows as input are actually the separate training instances. And those rows get maintained as we go through this matrix multiplication. So represents the input. The output of the first layer is the output of the first layer on row 1. Row 1 of the final output is the y hat of the first input instance. The second instance input is represented in row 2, and you would find the output in row 2. The kth instance is in row k as the input. All along the way, we look at the activations. Those are in row k for that. And in the final output, it's in row k. So this is how things are really calculated. We, instead of doing this entire process for a single training instance, and then the next training instance, the next training instance, we actually take, well, let's call them mini batches. Okay, so we'll take a mini batch of training instances, and we'll feed them all through this together. And then we'll have these k outputs. We'll then compute for each of those k instances gradients and average them together. Why does this matter so much? Well, because GPUs are ideally suited for doing matrix multiplication. So what we can do is, as long as we can fit all our matrices into GPU memory, right? A GPU is the graphical processing unit, which was designed for basically playing games. Right? So doing shading and all sorts of manipulation for doing graphics. It turns out it's very well suited for our matrix multiplication that we're doing here. So that was a real key insight that happened around 2012, 2013. Someone said, hey, we could start doing this neural network calculations actually on a GPU. And that's part of what's led to the big rise of deep learning. But in any case, the GPU, as long as you can fit your input matrix and all the intermediate matrices in the GPU memory, then it's just as fast to be working on K training instances as it is to be working on one instance. And that's really the trick to do it, is just stack them. And then they'll be operated on in parallel.